All right, so for this next section, we talk about combustion and combustion energy. Cool. So this is our chemical reaction. We saw this once before, right, when we did fire, yeah? Here we're going to be focusing on a different part, right? So you have some sort of hydrocarbon, right, plus oxygen, which you need, right? We talked about the fire triangle and how oxygen was one of them. Well, this is why the reaction needs it, right? You got fuel, which is a hydrocarbon, plus oxygen, and you put them together and you give it a spark, be able to get it over the hump and get it rolling down the hill, right? The activation energy in there, and it releases carbon dioxide, H2O, and energy which can then go back in and be its own spark, right? And this keeps happening over and over again in a loop, which is why the fire keeps going for as long as it has fuel and oxygen, right? Carbon dioxide smoke comes out, water vapor comes out. You got heat, energy, and light released. Awesome. We're going to focus on the hydrocarbon part, right? Not the fire part. So a hydrocarbon is exactly what it sounds like. Yeah. So you have some sort of chemical compound, could be a liquid, could be a gas, usually going to be one of those two, that is made out of two things, right? Hydrogen and carbon. Hydrogen could really be thought of as like a carrier, like a +1, I don't know, is the best way that I think of it, right? A +1 energy unit on top of the structure and the important part that comes from carbon. And why does carbon give them the structure? Because it forms things that no other chemical element forms. These things called chains and rings, right? Rings like this, yeah, or long chains. And carbon, part of what makes it so special and why you can form life out of it, is because you can essentially build these structures as big as you want. Now, living things have chemical compounds that are way more complicated and way longer than this. But they're made out of carbon rings and chains, just like the hydrocarbons are. Okay, 3 kinds of hydrocarbons that we're going to be familiar with here, right? We got coal, oil, and natural gas, right? The pictures kind of do an okay job here, right? Coal, you've got a tiny black rock. When you burn it, it releases tons of energy, right? It's by far the oldest one of these to come into widespread use, and the one that is being phased out the most, at least in the developed world these days. Oil, right? The black, thick, sticky stuff that if you strike it, you get rich, right? Comes in those barrels. Natural gas, totally invisible, used for heating, has less of an impact than these others, but also can't be used for things like making plastics the way that oil can, right? How are these formed, right? You got 5 steps to becoming a fossil fuel. All right, so the first step is be alive. Got it. Next, die. Next, get buried in some kind of an environment where you are not exposed to this thing, oxygen, right? It's a messy you-know-what that lives for drama of the chemical world. You don't want to be exposed to this while you're down there chilling, all right? So you're living, you die, you get buried in an environment where there is no oxygen, and while you're getting buried, right, and you've got rocks stacking up on top of you and sand and other, stuff falling in on top of you, right? You get enough heat and pressure underground to where you get lightly cooked. Not like crazy, seriously. Okay, like medium rare to like rare is how much you get cooked. That's it. And then the last part, which is really important, is don't escape until human beings can come find you. Some millions to hundreds of millions of years later, right? And if you can do all these things, then congratulations, you have become oil, right? Now, despite the sort of joke that it's, dinosaurs are like animals that mostly become hydrocarbons, it's not true, right? Where does this tend to happen, right? Where you get buried in an environment where you aren't going to be eaten by something else or destroyed by oxygen? How about at the bottom of a swamp, right? So these trees die and they fall in there and they absorb some of the oxygen. But because this is like a swamp or, something that's not well circulated, it doesn't have access to another body of water, right? It's just like this stagnant, still pool, right? It sucks up all the oxygen and more trees keep falling in, but now there's no oxygen in the water to support it or to support life, right? And so the trees get down there and they don't decompose. They don't get turned into something else. They don't go through any chemical reactions, right? They just stack up as organic matter, right? Carbon and hydrogen, which trees have a lot of, stacking up on the bottom of the swamp, right? Trees die, they fall in, they don't get destroyed by life or eaten, they don't get reacted with by oxygen, right? And over time, more of them fall in and pile up, and all of a sudden, they get buried under sediments, right, and get pushed down into the earth, where they get cooked just a little bit and become coal or oil, right? Another visual to get it, right? So if we go back, and now, there are other hydrocarbons that form later, right? But as an example, so like the coal deposits we talked about earlier in England and the United States that fuel the Industrial Revolution, right, and lead to geology, all right, a lot of them are formed in this particular time period called the Carboniferous period, which is just before dinosaurs are even in existence, right? You've got big, giant plants, more giant than anything you can imagine. They die, they fall into the swamp, right? And they're not broken down there because it's an anoxic environment. No circulation, no oxygen. Over many years, right, they are buried underwater, and sand and silt and clay and piles up and cooks them ever so slightly. They say heat and pressure, I say cooks. My version is better. And it turns them into coal or oil or gas, right? In the case of oil or gas, right, that doesn't want to stay down in there. Okay, now the coal will stay down in there. It's not looking for ways to escape. But like oil is lightweight compared to the rocks, and it's under so much pressure. So if there's a crack here and, you know, it has a pathway, the oil is going to squirt out and it's going to be lost forever. Or, you know, the gas, right? If there's a way to escape and it's under all this pressure from the overlying rocks, right? It's going to squirt out and escape forever. So one of the requirements in order to get oil or gas is that that doesn't happen. And a lot of times, instead of being these kind of flat layers of stuff that piled up, for things like oil or gas, you need something that acts as like a net that essentially traps it. So you've got some sort of source rock below where you have the organics, right, and where it actually forms, and then some sort of higher unit up that blocks it from escaping. And then you go and drill down here, and you get it. That's how that works. There are many different kinds of coal. None of them are clean. There's no such thing as clean coal. If you hear that, that's somebody trying to exploit you. Okay. These are arranged in order of their quality, right? So you've got lignite coal, which is really low quality, low energy, and then anthracite coal, which is really good quality, good energy. And it is known for a fact that all of this kind of coal, the like good kind, all of it has been mined out. There is no anthracite coal deposit left in the world that you can go mine. All the good stuff is gone. Sorry, it was gone before you got here. Next is oil, right? So liquid phase stuff kind of looks like this. It's got all sorts of other things in it. It's not just one kind of chemical. It's a huge variety of really complicated ones. This is the famous spindle top, right? So you remember I was talking about how if you just give it a chance that it'll squirt out because it's under so much pressure? Well, that's what happens. That's not the norm. A lot of times, you know, the oil and gas is buried way deeper than you would think, right? But it can happen, right? Oh, yeah. And to clarify, crude oil is the same thing as petroleum. If you've heard those words and not really known, like, what's the difference? Is it all the same? Crude oil and petroleum are the same. Later, right, you take that oil, right, and because it's made up of all these different chemical compounds, some of it gets turned into some stuff. You could turn it into asphalt along with sand and gravel and, you know, put it on the road. Some of the really light stuff becomes jet fuel. Some of the even lighter stuff becomes gasoline, right? Some of it gets turned into plastics, right? And so it has all these different uses in different areas. Yeah. Oil production in the United States, just something that most folks don't realize, is actually at its all-time high right now. And that is largely due to oil that is being produced as a result of fracking in West Texas, which is some of the stuff that I worked on, right? Most people don't realize this, that the United States is producing more oil today than ever before, and kind of have a weird view of U.S. energy production in general. But by any standard, the U.S. is producing more oil and natural gas than ever before. World oil production has also gone up hugely. So we remember, right, that there were those oil lines, right, and gas lines in the previous chapter, right, starting in about the 70s. Well, you never get a shortage that isn't followed by a glut, right? You have a shortage of oil leads to a glut to follow. And actually, if we were to continue this line up, it would look like this, right? Sort of similar to what you see with natural gas. U.S. is also the world's leader in natural gas, largely as a result of fracking technologies. Russia is number 2 on this, so yes, it is a fascistic oil state, and there's no other way to say it. Iran and other countries in the Arabian Peninsula are also major producers of hydrocarbons, oil and gas. For a while back, especially here in the 70s, as a result of that crisis, there was this idea of like peak oil that, we were going to run out of oil in the ground, or that people were going to stop demanding it anymore. As you can see by the green curve, which is, the real world here, that's not true, all right? The idea that, we should be worried about running out of oil in the ground is a myth, all right? If we were to run out of oil in the ground, we would be completely exploding the climate and get ourselves killed. That is not going to be the problem. The problem is elsewhere. Awesome. Fracking, we don't really care about the details here, but essentially you can have units down deep in the earth that are not very permeable. They're not very sponge-like, all right? But they have a lot of oil and gas in them. And so the idea is that you pump in water at a really high pressure and you induce all these cracks in the unit, right? You essentially, make your own sponge, right? And then, as a result, all the stuff in it, the hydrocarbons, the oil or gas, is now able to migrate whenever you suck it out of it, right? So you pump water in to explode things, and then you suck the oil or gas back out, put it into tanks, and move it elsewhere. And if you're thinking to yourself, what about the well here? Like, what happens if the cracks? The answer is yes, it totally can contaminate this well. There's a huge environmental damage, right, that can be done by fracking. Not just contaminating aquifers and drinking water, which is common, but also things like earthquakes, which is especially bad in Oklahoma, right, where you had a lot of this fracking activity, right? This is a sort of graph of earthquakes over time, right? Oklahoma, okay, the long story short version, should not have earthquakes. It is not near a plate boundary. There's nothing there that would cause them, right? These are caused by fracking, right? So these are earthquakes big enough to feel. Notice, right, so we start fracking here, how the earthquake amount jumps up rapidly and never goes all the way back down to where it was before. This is human-caused earthquakes, and it is certainly possible to reactivate deep geologic structures there that remain active forever. So, good job. Yes, this thing, the steam engine. Okay, we're going to talk a little bit. Oh, it doesn't do the animation. Okay. Oh, it does do the animation. Awesome. So, about how this thing works, right? So, you have coal down here, right? Which is boiling water and creating steam. Steam wants to expand, right? So, it expands all the way up until it comes to the top there, at which point it triggers a release valve, which releases the steam, and then it comes back down. And while it's pushing it up, right, it pulls this thing up and down, which turns a wheel. And once you can translate this into turning a wheel, you can do whatever kind of work you want with it. The other thing we could talk about here is the way that a car engine works, right? So most engines use a 4-stroke pattern like this, right? So you have some sort of intake where you pull in the air and fuel mixture, gasoline mixture, right? This thing is continually spinning, right? It pushes the piston back up until it's really, really tiny, and here the spark plug hits it, causes an ignition, causes this to ram back down and generates the power which drives the vehicle. And then as the final stroke, right, as it pulls back down and then comes back up, it pushes exhaust out, right? And you put some of these together, give it some good timing, and you've got a car, right? Fuel economy for cars overall, as a matter of combustion, has been getting better. Why? Gas prices, pressure, right? Consumer pressure. People want stuff with better gas mileage for their own sake. Regulatory pressures are another part of that, and requirements that vehicles get better gas mileage, and hybrids and EVs is the last one. People can have hybrid vehicles that get better fuel economy than ever before. And with that, we are ready to move on to electricity.